pick up where we were yesterday, and we'll also have, it will be useful that you guys saw some of the tools in 2D TQFTs today, because we'll draw some very similar pictures, but with slightly different meanings. So I wanted to first start with a bit of a recap of where we got so far last time, and sort of where our ultimate goal is that we're trying to get to. So remember I said that the idea that we are trying to get to is this idea of topological recursion. And topological recursion is a tool to start from something that we call a spectral curve that has these two functions on them, x and y. There'll also be this other thing, y differential, called Bergman kernel. And once you have this data, we're going to spit out a family of differentials that are labeled by two integers, g and n. So back then it was probably a little confusing maybe what this g and n had to do. But what we noticed is that when we kind of went back to the origins of where topological recursion came from, which was matrix integrals. And it was a tool to compute certain observables or certain expectation values of matrix integrals, starting just from very, very simple data. Okay, so topological recursion is going to be a way to start from basically just knowing the leading answer for a one-point function. And it's going to allow us to calculate all the observables that we want to all orders in 1 over n. So remember, n was the size of the matrix. And in particular, what we found is that there's a deep connection to this 1 over n expansion and to topology, okay, which is where this topology in topological recursion is coming from. So in order to see that, we had to introduce this whole notion of Feynman diagrams, which hopefully you remember a bit of. But today that's not going to play a huge role. What you're really going to need to take away is basically the observation, once we had this whole Feynman diagram technology, as to how the 1 over n expansion had to do something with topology, which was that if we looked at a expectation value of n traces, we could expand it in 1 over n, and we found that there's a 1 over n expansion that goes as such. And this G really had to do with the genus because they were the genus of the Feynman diagrams that we could look at. So we could just define what we mean by this by saying we're going to sum over all the Feynman diagrams of a given genus. Okay. Good. So in the big picture, what we did is we started from matrix models. Okay, we looked at the Feynman diagrams and the 1 over n expansion. And then we quickly saw that it's usually a hard thing to do to actually figure out all the Feynman diagrams and do those combinatorics, right? So what we wanted to do was to come up with some new tool which would not make us draw infinitely many pictures. And we found that there's a sort of clever technique that we call Schwinger-Dyson equations that allow us to give sort of consistency conditions between different expectation values. Okay, and it started from the idea that somehow the integral of a total derivative would be 0. Okay. And we got close to something that was called the loop equations. So we applied that, if you remember, for the expectation value of just one trace. And we derived an equation that we called the spectral curve. So I'll just remind you what this equation was. We found that this resolvent, which would be written as such, satisfied an equation, the genus 0 part, which was y squared minus v prime of xy plus a polynomial x is 0. Okay? So if we think of both y and x as complex variables, this defines a curve, a complex curve. Two complex things with one complex constraint gives us a one complex dimensional space. And that one complex dimensional space is going to precisely give rise to the spectral curve. It's going to define the spectral curve. Right? So this is a way that we started from some matrix integral, some RMT type of object that seemingly knows nothing about complex geometry, and we derived this special starting point of the spectral curve. Okay, so what we're going to do today is going to find a similar type of recurrence relation that tell us about how the other sort of more complicated expectation values like this are going to behave. Okay? So we're going to look at now the expectation value not just of a single resolvent, but of n resolvents. Okay? And in particular, we'll be interested at all genus G. Okay? So these will be the main objects of today's talk. And then we'll see that later on, there's a whole life that can be taken onto these, where that if we apply topological recursion to matrix models, this is sort of the dictionary. But these WGNs in other settings can be computing some totally different other thing. Okay, they'll be generating functions for some other observables you might be interested in. Okay, very good. Let me say one more thing a bit about the spectral curve. So one of them that we'll kind of work out through explicitly today. So we had arrived at this yesterday. So y squared minus So if the potential is 1/2 x squared, so this is just xy, and this polynomial for the GUE was very simple, it's just 1. And in particular here we can actually coordinatize, or we can give a parameterization for both x and y in terms of one variable z, okay, which will be basically a coordinate on the spectral curve. So let's just double check that this is indeed satisfying this equation. So we have y squared, z squared, minus x, so that's z plus 1 over z, times y, z plus 1 is 0. So let's check this. So we have z squared is going to cancel with this z squared. This gives us a minus 1 plus 1. That's indeed 0. Okay. So this is a first example where you see where we write x of z and y of z for z as single-valued coordinate on this curve. Note that x is not single-valued. So both z and 1 over z give you the same values for x. Okay. So this is, in terms of x space, x is a two-sheeted cover of the complex plane. Very good. Okay. So any questions about last time before we start about this material?
Are the x and y in the equation here the same as the x and y in the Sx, y, b?
Yes. Okay. Yes, exactly. So these are the x and y's of this spectral curve, and that spectral curve for the Gaussian, for example, here is written like that.
So all we're missing now is b, essentially.
We're missing b, and we're going to find that essentially b is just when g is equal to 0 and n is equal to 2. So we could go through a whole computation of that. It turns out for all matrix models, it's actually the same thing. So I'm not going to spend too much time on it, but that's what this b is going to be. Okay. So roughly, this y is going to be this w01. Okay, and this b, spoiling the story a little, is going to be this w02. And the idea is that once you have w01 and w02, this idea of topological recursion allows you to compute all WGNs. Okay, so that's a really surprising thing. Very good. Okay, any other questions? Okay, good. So we'll do things in a little less detail as we did last time. I could see your eyes glare over the indices. But sometimes it's good to get your hands a little dirty so you really feel with one example or the other that you really know what you're doing. Sometimes it's easy to convince yourself when things are very abstract, you've understood them, so you actually have to do a computation and realize you have no idea what's going on. So today we don't need to go through all the same sort of algebra, but I want to basically start from a similar type of Schwinger-Dyson equation and get to Einard-Orent and topological recursion. Now that could be itself multiple lectures, but I'll try to just summarize it in 4 steps for you. Okay, so we're going to do the same type of expressions. That we're going to start with 0 is the derivative with respect to MAB of this whole quantity here. Okay. So relative to what we did last time, I inserted some other extra traces. So that's what's new. And so, of course, the derivative can do 2 things. It can act either on this term, or on this term, and that will give us 3 different types of terms that can arise. Okay. So let me just tell you where each one of these is coming from. Okay, so we're going to have 0 is equal to where this acts on the first one. Okay, and that will be the same type of expression as we saw last time. So r goes from 0. Because I'm assuming everyone did all the exercises. Okay, so n to the and let me just use them all out. That's from acting on this first term over here. The second one is where this now acts on one of these traces, and it can act on any of those traces. So that'll be, can act on the jth guy, and the j can go from 2 to n. And when it takes this derivative, it brings down a factor of k, so kj. And then if you remember right, it fuses what's over here with the derivative. Just give you a trace n to the kj. I is not equal to j. acts on this guy. And finally, now there can be a last part, which is where it acts on the exponential, so it brings down a power of n, and then it's just going to give us a v prime that multiplies this. Trace v prime of n to the k1. Okay, very good. So these are the three types of terms that can arise. And this power of n, so we're not going to go through so much algebra, but this power of n is ultimately what's going to allow you to compute things that will really give you a recursion, meaning that there will be a recursion on the Euler characteristic okay, 2 minus 2 gun n. And as you can see, that's precisely what appears, as we saw yesterday. We always had n to the Euler characteristic of the surface. Okay, so this extra power of n is going to relate things that have different Euler characteristics, and that's going to give rise ultimately to the recursion formula. Very good. So we're going to do two other things. We're going to do just like we did for the one-point function yesterday, which is we're going to take this, and now we're going to think about connected correlators. And the second thing is we're then going to use the 1 over n expansion, and we're going to keep all the powers that are the same powers of n. So if you remember right, last time we had some various genus pieces, things simplified at genus 0. And now all I'm going to do is I'm just going to rewrite the same equation where I kind of keep track whether in a connected correlator this guy is with this one, or they're kind of both on the same correlator. I'm just going to write something here. You can ask me some questions. Okay. Any questions, first of all, about just what we did right here? So this might look like magic, but it's using the exact same expressions that I told you to derive yesterday. So that when you take a derivative here, you generate this term over here. When you take a derivative here, multiply it by that, you get this guy. Okay, so now let's just write this in terms of the connected correlators. And I'm going to move this guy to the left-hand side. Okay. And we're going to use that. Yeah. We're going to write, say, v of m. It's 1/2 m squared. So what this second step is going to do, this is step number 2. So now we're going to restrict to connected correlators. Correlators is kind of a physics term. By correlator, I mean these expectation values. And then we're going to use 1 over n expansion. Okay, and then we're going to keep terms with the same power of n. I'm just going to tell you the results. We don't need to totally work through that. So it's going to be the following. You know what? Let's make this also a little simpler, just to make notation a little easier. So I'm just going to call this, for a second, OS. Okay, just the OS. It's just these other traces that are hanging around. This hand. G, and this is going to be equal to, so there's going to be 2 types of contributions from this term. Okay, when we restrict to a correlator, remember we have to We have to check whether they're going to be in the same. So the type of thing we're looking at again is this connected. So let me think about this way. Yeah, it could be something like this. So in this connected piece, there'll be a part that looks like this, and a part that looks like this. The O and A, and there could be a part where they're all together. Okay, so we're just kind of going to keep track of where these two traces over here can sit in a connected correlator. Okay, either they're going to be both together in the same correlator, or they're going to be split. We're going to see what this means geometrically after that. Okay. So we have this. So let's say 0. So this is where they both sit together. Connected, but this is going to be G minus 1. It's going to be G minus 1 because there's going to be two traces sitting in it. So we're going to be keeping the same amount of things here where the total order characteristic is the same. Okay, so if we have more n's, we'll need less g's. So it's something that means this one. The part where these guys disconnect, so there can be. So here, they're going to be able to split into two things. We need the overall genus to actually be the same. So there's going to be a G1 and a G2, but we're going to need that G1 plus G2 is going to be G. And then there's all the ways of distributing these n minus 2 traces around. Okay? So we have n minus 2 traces over here, n minus 1 traces over here. And so we have to look at all possible ways that those can be split across this. Okay? So one way to write that is that we just look at two partitions of 2 to the n. Oh, sorry, 2 up to n, which again is just the number of these traces over here. Okay. So I'll call that OI and OJ. And of course, we need that the union of them is just the same number of traces that we started out with. And then, of course, there's still our final term from here. But we've eaten up the jth guy, okay, so there's no. If you want, you could do this as an exercise, but if you take the left-handed equation, you expand all the correlators and connected guys, you keep the same powers of n. These will be the only terms that have the same power. Okay. And then it's varied algebra. It's not too important, I'm just giving you this equation. Okay, good. So physicists knew this equation for a very long time. Okay. And in some sense, it's a beautiful equation, but it doesn't really allow you to compute everything. So, as we saw last time, a bit, sometimes with recursion relations, you still need to, of course, compute the base case of the recursion. And it turned out that there was a different base case for every genus G here. Okay? So, of course, it becomes very hard to compute at higher genus. And so one of the really brilliant insights of Eynard and Orentin was to find a way to massage this equation into a way that we can actually completely solve it. And so the first thing that they did was to write it not in terms of traces, but to write it in terms of the resolvents, which is also something we saw that we had to do yesterday, right? So you basically multiply by some inverse powers of x, and you sum over all possible powers, and you write this in terms of resolvents. Okay? So you can take this equation and then try to ask what is the equation in terms of these resolvents. I'm not going to write that equation down. It's very similar. Okay? The true insight was that these WGNs actually have some very nice analytic properties. Okay, so this is where the power of complex analysis is going to come in and allow you to actually solve these recurrence relations. So these WGNs, I'm just going to tell you their analytic properties. It turns out that as functions of z on the spectral curve, the only poles that they have are precisely at what are called the branch points of the spectral curve. So we're going to define what that means. So we have poles at branch points, or ramification points really, of the spectral curve. And I'm going to tell you what that is. I know we haven't defined it. With no residue. And it turns out that this is actually very, very powerful. So you're going to be able to use the fact that you're going to essentially use an analytic continuation, that if you know the expansion around each of these poles, you're actually going to be able to analytically continue these functions away from it, and you're going to know their behavior all over the spectral curve. Okay. So let me just tell you what these branch points are. So really the ramification points. So let me try to. They're going to be those values of z where dx of z is equal to 0. So just to make this a little concrete, so let's go back to our GUE spectral curve that we had over here. Okay, so x is z plus 1 over z. So what would those be? GUE. Okay, so we would take d of z plus 1 over z. Okay, so that's 1 minus 1 over z squared dz. dz is nowhere vanishing, so where is this 0?
Plus minus I? No.
Minus 1.
Plus minus 1. Yeah. Okay. So here we have the z plus or minus 1. So that's going to be a very important feature that allowed Eynard and Naranton to write a recursion relation directly for these WGNs. So I'm not going to go through the algebra of how we start from here and get to Eynard-Naranton topological recursion. I thought a bit about it, but that really requires a lot of time, and I don't think you would get that much out of it. Okay. So I'm just going to tell you the answer. But first, any questions about what we just did?
One quick question. Is there a geometrical signification for these ramification points? Is it where the curve is kind of flat or something?
Yes, right? So this is precisely where basically x is not changing anymore.
Okay.
It's also where the two sheets of the two covers of the complex plane are basically moving along a cut, and this is the endpoints of the cut. That's helpful. For people who think a bit about RMT, let me just mention that I'll get to your question, yeah. In terms of x, we can ask again, so yesterday we looked at this function y as a function of x, not y as a function of z. Okay. And we found that what it looked like was x minus x squared minus 4 over 2. So the branch cut comes precisely from this square root over here. And the endpoints of the branch cut are x equals plus or minus 2. And as someone maybe mentioned yesterday, the discontinuity of y across the branch cut turns out to give you precisely the density of eigenvalues of this random matrix. Okay, so maybe for people who've seen this picture, if you haven't seen this picture, it's not too important. But this Wigner semicircle that we mentioned yesterday, you can ask what is its width, and that's precisely plus and minus 2. So the eigenvalues are supported precisely on the cut, and the endpoints of the distribution are precisely these points here. So they are special points. Yeah. This was quick. Only if you know RMT, maybe that's helpful, and if not, don't worry about it. Okay, any more questions? Yeah.
So you keep saying spectral curve, but as far as I'm aware, like this is a geometric structure in x1, up to the n, so it lives in c to the n. So
No, this X lives on the spectral curve, so it's on n copies of the spectral curve.
I see.
So it's going to be a symmetric form on S. Right? So this is not going to be wedged together, but it's a tensor product.
Gotcha. Thank you very much.
Good question. Okay, anything else?
In the second term, when decomposing the expectation value,
Yeah.
why isn't it like K1 minus R?
Oh, it definitely is, sorry. Yeah, it's just the way of splitting these two terms.
Okay, I just wanted to make sure. Okay.
Can you say again what is analytic property is useful for us? Like this pulse that is...
Yeah, it's going to actually allow us to solve this recursion in terms of these WGNs. So remember yesterday there was this polynomial P of x that appeared? Turns out that P of x doesn't have any poles at these branch points, whereas these WGNs have poles only there. And so there's a way of kind of massaging this equation to actually drop that P of x at higher genus. I think we wrote the equation yesterday also for higher genus for the 1-point function. And there was a PG of x, which was the expansion of that polynomial in 1 over n.
Yeah.
So we have this thing. Right. We had that polynomial, and so the way that physicists were stuck is that it still required you to compute something in every genus. And by essentially, we're going to take some residues of some basically rewrite of this equation, we can actually drop that term because it doesn't have any poles.
Okay.
That's basically the main idea behind inordinate. So it's very clever. Yeah. Right now this all seems kind of a little trivial, like what is this going to value? But it's really that this combination of the traces has nice analytic properties.
Why did you wrote no residue? Like you have poles at the branch point?
They have no residue. And when this curve itself can have a higher genus, which can happen, you also need to know something about the integrals, the period integrals around, say, like A of the cycles.
Yeah, I was just about to say, so these are like differentials of the first kind, but then you'd have to consider second and third kind if you went to higher G.
Yeah, so for example, that B is going to be of second kind. Okay. Any other questions? So far, so good? Okay, so as I said, we're going to do a bit of a leap of faith, just to spare you some algebra on a Friday afternoon. And I'm going to tell you that you can transform this equation into what is known as Einard-Arendt topological recursion relation. Okay. And this K is going to be what's called the recursion kernel. And after we draw some pictures, I'm going to tell you how it's built out of the data of the spectral curve. But basically, this recursion kernel is completely built out of this y and this b. Okay, so once you have this y and this b, which correspond to a 1 and 2 point function at genus 0, you have all the data you need to then build this recursion kernel. And now let's check that there's actually a recursion going on. Okay, that's maybe the first thing. If I tell you it's a recursion relation, let's check it's a recursion relation. So what is it a recursion relation on? So I've kind of already mentioned this, but let's see if anyone sees.
On the genus?
So it's not quite the genus because, as we see, there's a G here. But there's different powers of G that can mix over here, so that's not going to quite be correct. Yeah. So for example, how would we interpret this equation at genus 0? Okay. So if we have g is equal to 0 over here, okay, there's no g minus 1, so we can drop that piece. But then we could have g1 and g2 both be 0. Right? So g1 and g2 are 0, they sum up to 0. So that would tell you that you need all the genus 0 data on the left-hand side. So that's not a recursion on the genus yet. So let's look at this combination that I was mentioning, which is the Euler characteristic. Really, it's minus the Euler characteristic that we're going to look at. So I guess this way. Okay. So let's compute it over here. Okay, so on the left-hand side, so what we have, 2g. This green is bad, right? Forget. This green is okay? What is bad? It's the blue?
Yeah.
Okay. So we have 2g minus 2 plus n. And let's look at this term. Okay. So what do we have over here? We have 2 g minus 1 minus 2 plus n plus 1. Okay. So as you can see, that's going to be cut. So that's 2g minus 2 plus n minus 2 plus 1. So it's a minus 1 left over. So this guy has 1 less of the Euler characteristic. And you can convince yourself that that's also true for these terms over here. So that's why it's called topological recursion, because it's about this topological invariant, which is the Euler characteristic. Good. So let's draw some pictures to get a bit of a feeling for what this equation means. And then we'll try to explain what those pictures are in equations. Then we'll actually give us some examples, and then we'll see how you actually use this to compute something. Okay, we'll reproduce some of the examples that we already had from Feynman diagrams yesterday. But then we'll do things that are much harder that we were not able to do with Feynman diagrams. Okay? Great. Just kind of like that. So it's a recursion on this term. Okay. So I'm going to draw this recursion kernel as something that looks like this. Okay. With a pair pants diagram. I'm going to call this K. And these WGNs, I'm going to draw them as a surface with genus G. So in this case, G would be equals to 2. And then there will be n marked boundaries, just this n. And I'll call, say, this one 1. This will say be 2, 3, up to n. Okay. So this recursion kernel is going to have a label 1 over here, so that's Z1. And then the residue that we're taking with is with respect to this unlabeled guy Z. Okay. We'll call this Z. Now we're going to need to introduce something which is called the local involution of Z around the branch point. So I'm going to call this Z bar. It's not the complex conjugate in this case. What is it? So we will just go back here. It's that around each branch point, when there's simple branch points, okay, I could go into explaining what that means. It just means that locally that there are 2 points, Z and Z bar, such that around the branch point, it permutes them. Okay? So in this case, we have something even simpler, which is that Z goes to 1 over Z is even a global evolution. Okay? Right? Just from this, you know that if I took Z or 1 over Z, I get the same X. Okay? So for this matrix model, in this case, the Z bar just means 1 over Z. Sometimes we call this also, you might see in the literature, sigma of Z, local involution. Okay, so that's going to be what this K is. So what can happen is that we can basically build this surface in 2 different types of ways. So one, we have 1 less hole. Well, the genus is smaller, but we have more marked points. So we can have something like this going on. So this would have genus 1 in this case. And as you can see, as I'm going to glue this together, it's going to create another hole. So it gives us another genus. So that would be this guy over here. But there's another way that we can do this, which is when we're going to glue 2 disconnected pieces to these 2 legs over here. So we're going to sum over all possible ways, g1 plus g2 is g, and all ways that we can distribute the n minus 1 boundaries. So let's draw this as a picture. So, you know what, I'm just going to draw this recursion kernel maybe twice. Is it clear to you that this guy is going to act on over here? Okay, good. So there'll be 2. So we can do something like this. So we're at 3. Something like this. So this will have genus G2. This will have genus G1. All right, here. Genus G2, genus G1. In this case, something like that. And then this will have Z, sigma of Z, glued over here. And this will have I and J marked boundaries. Okay. So we'll do some examples. So it's just all the ways I could distribute 2, 3, 4 across these guys. Okay. So the first boundary will always be over here. And I could have maybe 2, 3, and 1. I could have 1, 2, and 3, etc., etc. And I sum over all the possible ways.
Sorry, is there a reason why the orange picture is drawn in that singular way?
In this what?
In this singular way where the two...
Yeah, because it's not equal to W03. And it's the fact that these are not independent variables. So this is Z, and then this is the sigma of Z. So they're not different boundaries. So they should, and in particular, they actually become singular as you go to the end. They become the same. So it's kind of more like almost like a contact term type of interaction we would think about. In some sense, it's like a geometric type of OP where 2 guys are fusing into 1. But it's not the TFT type of W03 that we think of. Yeah. Okay.
And maybe sorry, we just don't... so is this thing so far for a general potential, or are you taking that...
This is going to turn out that this type of equation holds way beyond matrix models. Okay, so that was the next kind of big insight of Leonard and Laurentien, is that even though we're starting from matrix models and we derive such an equation, it turns out this type of recursion relation is very, very general. So once you start putting x's and y's that you kind of just get to pick, you get a very, you can always compute these WGNs in this way. Right now we're looking at them for a particular type of matrix model. But a particular type of matrix model just means picking a particular x and y. So this is a very general formalism. But I'm motivating it to you the way it was discovered from matrix models. Okay? So now let's put this a little in equations. In particular, I haven't told you yet what this recursion kernel is. Okay, so we want to define that in terms of this basic data, x, y, and b, that are needed when we define this matrix recursion. Okay, so what is going to be k? So this k, z1, Z1 and Z. 1/2. Okay. So we're going to use this Y. And now X, it's going to be differential dx of Z. And on the top, there's going to be this B. So this B we haven't discussed. This B, well, let me just first write down the equation. And then we'll write Z, Z, B of Z1, and let's call it, so in this integral, I'm integrating with respect to dw. Okay, so I'm going to do this integral up to Z, where the 2 boundary conditions are Z and sigma of Z. So let me tell you what this B is now. So this is just to tell you that these pictures are going to be kind of equations. Okay, this kernel is written as going to be some function, meromorphic function on the spectral curve. So as a function purely of Z. And then this residue we're going to take with respect to Z. So we'll build up some few examples slowly. But this is just to tell you first of all what that is, and let me tell you what B is. Okay.
Along what path?
That doesn't matter.
Oh, it's going to end up after that. Okay. Good.
So I'll first just define B, and then I'll tell you what it has to do with the two-point function in a matrix model. So this B, for all intents and purposes, is what's called the Bergman kernel. Well, that's always true. Let's forget this one or two ends. One? One, yeah, thanks. Okay. So it's going to be this B, Z1 and Z2. It's going to be a differential in Z1 and Z2. Okay, so you should think of this as a tensor product here. And it has a singularity when Z1 is equal to Z2, double pole like this. Okay. So for all the examples that we'll use today, this is what we'll use. There's more general choices of Bergman kernels. They're usually heavily restricted, and they depend a bit on the periods of the spectral curve. If this spectral curve itself can be some higher genus Riemann surface. So not the same Riemann surfaces that we were talking about with the Feynman diagrams. It's just that this algebraic equation, it defines this 2D surface, one complex dimensional, and that itself can have a genus. Okay, so totally different notion of genus.
Maybe it's a basic question, but how do you divide by one form?
It's because there's going to be some two forms up here and some dx's are going to cancel. This is a rigorous mathematical subject that was invented by physicists who became mathematicians. So there's things like dividing the dz's all over the place. Very good. Okay.
Did you all integrate over the dw in this context?
Yeah. So we'll work this out. So what we're going to do is I'm going to first kind of tell you this general picture, and by the end of the class, we'll actually work out some of the WGNs for the spectral curve of the Gaussian, and then maybe even this quartic matrix integral. And then we'll see this all kind of work really in practice. Okay? But we're just building up slowly. So what does this Bergman kernel have to do with matrix models? This Bergman kernel is going to be related to W02. Related to W02. Okay. But it's not going to be exactly equal to the two-point function of resolvents. It's going to be, I think maybe it's time to have some fresh boards. And we can do a break again around 5:15 like we did yesterday. How it relates to this two-point function. This Bergman kernel is equal to these resolvents that we've been looking at. I can also write x1 of z1 and x2, but I'm just trying to simplify some things. Plus x of z1.
Isn't g equal to 0?
This is g equals to 0. This is g equals to 0. So it's basically the resolvent up to this shift. Okay? If you're really interested, ultimately where that comes from is actually precisely from this term in this equation. but it doesn't matter too much. Just so that you know why this shift appears. Okay, it comes from that extra term. Right? So if you go back now, this type of term is like this guy over here. This split in G1, G2 is like this guy over here. And so this extra term is the one that you don't see immediately in our topological recursion, but it basically ends up giving this shift over here. It gets reshifted into that. Okay, very good. So we have all the ingredients. We've written down what the recursion relation is. We've understood what it's a recursion relation on. We've written down what this K is. I think it's maybe useful, at least for me it was helpful, to write out a few examples, okay, of seeing what that equation precisely means. And then what we can do is we can take a particular spectral curve, like for this Gaussian, compute this K, and actually try to run this recursion relation. Okay, okay, very good.
Yep. Say a word about the residue, because this residue is
Ah.
an n+1 form, it gives back an n form, and you only vary z? Or?
Yeah, so you're only varying z. Yeah, so the residue is going to be with respect to z. These residues, sorry, I didn't at all say where we're taking the residues over. So what are these points? These are precisely at the ramification points of the spectral curve. So again, so where dx A is 0. Okay, that's where we're taking these residues. I think, yeah, you'll see that, so in the residue, there's always going to be an extra dz that we're integrating over. That's going to be the extra dz, I think, that you're worried about. Okay, good. So,
is there some limit? Because you say z goes to a, or?
Oh, it's just the residue at z equals to a. Okay, so let's just write out a few examples and the pictures that go with it. Okay, so let's just do some examples of this TR equation.
So just a question on the Bergman kernel.
Yeah.
So which is the definition? Is it this one here or is it that one there?
Those are the same things, it turns out. So it turns out that for all matrix models, when you write it in terms of z, it always looks the same. It's a really beautiful fact. It's not trivial. Okay, so let's do an example. So we would have W, let's do W03 for example. I'm gonna have this guy, this. So this will be 1, 2, and 3. So this we can write as a recursion kernel. Okay. And so what are the only things of genus 0 that will have 2 points? Well, it's basically this Bergman kernel. Okay, so that's going to be this W03. So we can have a guy like this. Z, Z bar. This is Z1. And now this could either be Z2 or Z3. Or we could also have the swap, right? So we could have this guy. Where's my watch? We had 1, 2, 3. But then we could also have so that tells us that W03, Z1, Z2, Z3 is going to be computed as the residue. Z is A. And we sum over all these branch points. Z1, Z. And now here this is this Bergman kernel B. Okay, so W02 B of ZZ2 B of plus the symmetrized scatter. That's our first little example.
What happened to this extra term in the Bergman kernel?
What do you mean?
This dxz1, dxz2 that we added like at the end.
Yeah. So I'm saying that what you need to do is you need to replace W02 by this B. It keeps track of that one other extra term. So whenever you see a cylinder, you put B.
Okay, but like the cylinder will be just like the expectation value at g equals 0, right?
No. By this cylinder, I mean this.
Okay. So it's not like you said before, W.
No, that's the relationship here. Yeah.
Okay.
So the two special ones are W01, which is Y, and W02, which we're going to replace by B.
So we just replace it by b.
Yeah, just replace it by B. Think of it that way if you want. So this is all data that we already have. Okay, this is low genus data, and we can compute this guy. So we're going to do this computation later, and we're going to be able to, for example, compute a 3-point function in this quartic matrix integral that would have been incredibly hard to compute. You would have had to draw infinitely many diagrams, okay, with 3 external vertices and infinitely many internal vertices that came from expanding the potential that we did yesterday. It'd be impossible to do all the combinatorics. And this would be a very simple residue integral to do.
We're missing a bar in the latter two
Yeah.
B's.
There's a bar here. Okay, let's draw another one maybe. So a simple one already at higher genus. Okay, just trying to draw some examples for you guys. Get a little intuition for how this works. And I think it's better for us to spend some time drawing pictures than to actually computing residues. So those I will just give you. But this is the type of thing that you can really automate on Mathematica, for example. So there are nice packages for topological recursion that compute these residues integrals for you. They draw all these pictures. Well, they basically, they know how to write all the things that they need to compute on the left-hand side. Okay, let's do an even simpler one maybe. So our first higher genus thing, n equals to 1. Is that right? Okay, so what is this? This is a torus. So we have 1. So how do we build that out? Okay, so we've got our recursion kernel. So what do I glue to this?
Half loop.
Exactly. So I just basically take that same cylinder and then I just kind of wrap it around like this. Okay. So can anyone tell me in equations what this means? Residue over all the branch points of this curve. So in the GUE, that would be residues at z equals plus and minus 1, and we sum over both of them. And this recursion kernel, z1 and z, and then what is this?
E of z, z bar.
Exactly, very good. B of z, z bar. Okay. So you can see this is actually a very quick way to already compute something at higher genus, right? This would, for example, resum all the diagrams that have the topology of a torus, we're going to see. Okay, so that's actually, we only saw one such diagram yesterday, and this will do all the diagrams for us in one go by doing a simple integral. We'll do one last one, just so that you guys understand all the permutations. So what happens for, let's do W e equals to 0, n equals to 4. 1, 2, 3, 4. So what happens now?
We draw K.
Okay, we draw K, exactly. Okay. Z, Now what am I drawing?
Cylinder and another K.
There's always just one K in this equation. There's always just one K. So there's never multiple Ks that appear. Good guess, could have happened.
We draw the first example.
W03? Yeah, very good. W.
The whole cylinder at the bottom.
And then a cylinder at the bottom.
Versus the other way around.
And how many ways are there of doing this?
Yeah.
So that's true. So there's also going to be the one where I have a cylinder on top and this guy over here. Is this it?
4, maybe.
So we have to be careful because we have to distribute all the boundaries across, right? So for example, if I have 1 and 2, then this guy would be 3. But there's the same diagram where there's this guy. Cylinder. But now we have 1 and 3, and this guy would be 2. Again, of course, there's always a k multiplying this.
I guess it's 2, 3, 4 because we started with 1.
Oh, sorry. 2, 3, 4. Yeah, so, yeah, what did I do here? Sorry. 2, 3, and 4. Okay. But there's also, for example, 2, 4, and 3. But there's also 3, 4, and 2. And then, of course, what we can do is we can take the same permutations, but now we switch with the cylinder on the top and W03 on the bottom. Is that clear? So you really have to sum over all possible ways of splitting up that surface. Very good. So in particular, if you had forgotten those permutations, you would get the wrong answer. So one thing that is clear, let me try to maybe emphasize why that has to come out symmetrically, is that, oh, sorry, where did we, remember that these WGNs, they're just a product of n resolvents, okay? So you can move them around in the expectation value, so everything has to be symmetric. So one of the things that's happening here is you're just making sure that everything is symmetrized on the boundaries. Okay, very good. So maybe this is a good place for us to stop. And what I'd like to do when we come back is to try to put a little meat on these pictures, which is to compute in say the GUI case, and then we'll write down some answers for the quartic, which is to actually just kind of write this out. Okay, see what this looks like as a function of z, do a residue, and see how we're going to get the same thing as, for example, our one-point function at genus 1 that we computed yesterday. Okay? When we looked at trace m to the 4, we had 2 genus 0 contributions and a genus 1. We had this torus diagram. So in fact, we want to, for example, see that torus diagram appear, but now from these functions, these generated functions. So, any questions? Yeah.
To some extent, Hakim was actually right, because like when you compute omega 04, you have omega 03 appearing, so you could actually immediately I mean, if you insert this equation, you actually you get a second.
That's applying the recursion just further. So that's the sense in which, at the end of the day, you just keep breaking things down to k, b, and y. Yeah.
What is y?
So y appears basically okay. So let me just say b in this recursion kernel. Yeah.
So just to make clear, like all of these 1, 2, 3, they are points on the spectral curve essentially.
They are coordinates, so they're z1 through zn. So these are functions on the spectral curve. So they're functions of z. In particular, they're differentials.
Right. And I'm still not a bit clear about the question I had before. You mentioned at some point that this omega, what will be here, 02, which will replace by b, you mentioned it's not exactly b because of this extra term we add there.
Yes.
Why do we just...
Yeah, because of this.
Exactly.
Yes.
So why do we just can replace it b in these equations then?
It's literally to write, in order to write the equation that we had before into this form, there was a third term.
Oh, and that...
Just like that,
Okay.
and that ends up basically shifting this b.
Okay, okay.
Roughly.
Roughly, okay.
But that's more of it. Do you understand the main logic that we're trying to do? So we have these complicated combinatorics problems of trying to draw these graphs, and they get very hard very quickly. And it's going to simplify these combinatorics problems extremely by reducing them to do a single residue integral. Okay? So that it's a very, very powerful tool. It's things that we would not know how to do to enumerate these graphs. And the power of topological recursion is that it turns out it solves many, many enumerative geometry and combinatorics problems. So usually, once you have to solve a simple-ish problem, which is to find the spectral curve. So you find this y, this x. B is usually kind of always the same, somewhat magically. And once you have that, you basically can solve the entire problem. You can compute very complicated things, from Hurwitz numbers to topological string amplitudes to whatnot. It's a very, very powerful formalism. I'm just trying to give you an example of what it solves in the case of matrix models.
Stupid question now. What do we do next with this omega? Like, there are differentials on this curve, or like with coordinates on this curve.
Yeah.
What do they help us with?
So we'll see that in the next, after the coffee. I think everyone needs a little coffee.
Yeah, fair enough.
So let's take a break for about, let's say 20 minutes, 25 minutes. Okay guys, so let's restart. Let's restart. So I first want to address one of the questions that came up at the very end, which was, okay, once you have all these WGNs, what are you going to do with them? Okay, so we're making all this fuss about how we can compute them. How are they useful to us? Okay. So let's just try to remember the relationship between the resolvent and the single powers of traces that we wanted to compute. Right? So what was trace 1 over x minus m? Okay. This was a power series in 1 over x to the k plus 1, trace m to the k. So if I wanted to extract a particular trace m to the k, what sort of operation could I do? I want to extract one particular term in this sum.
A residue.
I could take a residue. Right? So for example, I could take a residue of x to the L around x to infinity. Because when I have x over, times dx. So what we could do is multiply this by x. I'm missing a minus sign. Minus sign. But now note that this is actually precisely what is hiding in the WGNs, right? So remember these WGNs are these differentials. So 1 to n trace dxi over xi minus m. So if I take residues with respect to x goes to infinity and I multiply some particular powers, I can always extract the correlation functions, trace m to the L1, trace m to the Ln. These were connected, a genus G, so these are genus G connected correlators. So again, by taking x to the L1, x to the Ln, I take residues as all of these guys are going to infinity. Now for x equals z plus 1 over z, I have a choice as to what I'm calling, say, the physical sheet, which is either saying z goes to infinity is x equals infinity, or z equals 0 is x equals infinity. So we can make a choice. You have to be consistent in your conventions. So for example, what that's telling us is that I write all of these guys as functions of z. But now these are residues at z equals to 0, not at the branch points of the curve, right? And so this will extract for us precisely these observables. Okay. So this is just another restatement that the correlation functions or the expectation values of resolvents are generating functions for all of the expectation values we wanted to compute and that have a nice diagrammatic meaning in terms of the contractions. Okay. So does that answer your question earlier? With out of the WGNs, how we encode the information? Okay. So this is also why once we have them as functions of z, right? So these are functions of z1 through zn, we have all the information we need.
Why do you need the dx again? Because in principle you could also take the residue of just, instead of dx over x minus n, you have 1 over n.
Yeah. Well, a residue is always an integral. So when we do something like that, we're doing an integral with respect to some measure. I'm saying that measure is dx. Okay. So in particular, I didn't write the residue here because it's already hidden in this dz. So here I didn't write an extra. Yep. Okay. Very good. Okay. So, well, actually, I could have left that. Yeah. Okay. So now what I want to do is to try to use this in practice a little. Get our hands dirty, compute at least one example, and kind of see how this really works and how we reproduce some of these Wick contractions that we saw yesterday. Okay. So that it feels a little less like some abstract mumbo jumbo and something that really works and is powerful. So we'll first start with the Gaussian matrix model from yesterday. So again, we're going to do the Gaussian matrix model. Okay, so again, the type of integral we were looking at was this guy. And from here we found the spectral curve y squared minus xy plus 1 to 0. And that we can write in terms of x of z is z plus 1 over z, and y of z is just z. Okay. So let's take this as our data, and again we're going to supplement it by this Bergman kernel. Easy. I'll call it maybe C1, C2. Z1 minus Z2 squared. Okay. So this defines the spectral curve is given by this. We want to see how we spit out the higher WGNs, and we can actually check some of these traces. Okay, good. So then let's just look at this kernel, and let's compute what this kernel is. Okay. Let's do some of these computations. Okay, so the integral, so what was this sigma of z in this case? And why was that?
Because it's this point in that x of z thing.
Right, so we need the x of sigma of z is equal to x of z around each point. Okay. But in this case, that's actually a global thing, because if I replace z by 1 over z, 1 over 1 over z is z, I get the same thing. Okay? So in this case, sigma of z is just 1 over z. integral up to z of this Bergman kernel. So we have dz1 dw over z1 minus w squared. Okay, so we can just do this integral. So the integral of 1 over z1 minus w squared, evaluated at z. So there we have a dz1. That one just comes from the right. z1 minus z minus dz1 over z1 minus 1 over z. So particularly this on top, this looks like that. Over z1 minus z, z1 minus 1 over z times dz1. Just put the two fractions together. Okay, very good. So now let's build this kernel. Okay, so this k of z1 and z, this is the numerator. Okay, so we have 1/2. The numerator we already have. Okay, so I'll write that right over here. And over here we have y of z, so that's z, minus y of sigma of z, 1 over z, and dx of z, so d of z plus 1 over z. Okay, so notice actually these terms cancel, and this just becomes 1 over 1 minus 1 over z squared, z1 minus z, z1 over z, dz1 over dz. Any questions about?
We're missing a half.
With the half, yeah. So that's what we mean by this recursion kernel K. So let's now compute our first homogeneous thing using topological recursion, which we wrote over here. Okay, so now we can plug this in. So here we have the picture. And now we're going to do our first computations here. So what do we need to do? We need to take a residue. So we have W, T equals 1, N equals 1 of Z1. This is the residue. Where do I take these residues?
It's minus 1.
Okay, and why was that?
Those are the points of the curve, yeah, the ramification points of S.
Right. So when I, yeah.
On the other
We
board.
take this, we get 1 minus 1 over z squared. Where does dx vanish? Precisely at z equals plus minus 1. Right? So we get a sum over a equals to plus minus 1. And we're taking the residue at z equals to a. Okay. So we have this recursion kernel. 1/2. Let me multiply everything by, let's say, z cubed, just to make everything nice. Maybe let's put a z cubed up there. Got z squared minus 1. dz1 over dz. Okay. And now, how about this recursion? How about this b? Okay. So this b, right? So this is dz, d of 1 over z, z minus this guy, 1 over z squared. Okay. So if we just go back to the definition of this Bergman kernel, which we don't have here. As plug in W equals to 1 over Z. Okay. So you can see up here I'm going to get a dz squared, right? In the denominator I'm going to get a dz over z squared times dz. So note that this dz cancels with this dz. Oh, come on, that's fine. Really? This is where you get riled up? You guys are going to have harder things in life if you continue in physics.
I'm proud.
Okay, so this, what you can now see is that we're actually just doing a single integral with respect to dz. So there's nothing, and dz1 will give us what's going to be giving us the differential in wgn of 1. So I could make you guys compute this. I don't think we really have to go through that. We'll write them down. So the first residue at z equals to plus 1 is equal to z1 squared minus 4z1 plus 1 over 32 z1 minus 1 to the 4 dz1. And there's the second residue at minus 1, which is just giving us a minus sign. And you can combine these two things in your free time. You'll find that this is equal to cubed over 1 minus z1 squared over 4 dz1. So just to show you that it's very concrete, okay, we can do this. So now let's check how this actually reproduces the first Feynman diagram that we saw yesterday. So remember, yesterday we computed trace m to the 4 in the GUE, and we had these 4 type of diagrams, right? So we had these 2 ones, which were planar. Oops. And then we had this guy that was non-planar. So we said this you would have to draw on a torus, right? So this told us that this was trace m to the 4 at genus 0 was equal to 2. That's what these 2 diagrams were doing. And trace m to the 4 at genus 1 was just equal to 1. There was just that single non-planar diagram there. This was from yesterday.
So where did the other dz go? We have dz1. Where did the red one?
So we have a dz squared. So these cancels.
No. And the final answer we have.
We're doing an integral with respect to dz.
So so it's not actually taking the residue, actually taking the integral.
By this residue, I mean I'm doing this integral over z equals to a dz.
Okay, perfect. Just
So
making
I'm
sure.
integrating with respect to z, so of course it's not there anymore. It's in the final answer. Okay, I'm seeing some puzzled faces, so let's slow down. This is mostly algebra, so just ask me any questions you have about this. Okay. Was the construction of the kernel clear? Once we have B, right?
Fine and dandy.
Just do an integral, okay? Then we had y minus y of z dx is in the definition of the kernel. And this just gives us now this very explicit kernel. And now we took this kernel here, we just put it right there, and this tube, which is represented by this b, that's right here, and then we just took the residue. Okay, so I didn't go through it, but you can expand it in powers of z minus 1, etc. mathematically do that type of work. Okay. And then I just combine the two values at the two residues. So this was the residue at z equals to +1, and the residue at z equals to -1. Okay. So now what we want to do is we want to see how this compares. So just given what we said earlier, right? So now we have an explicit answer for WG1 n equals to 1. And now we want to use this. Okay? So we want to take a residue at z goes to 0 of x of z to the 2k, and that'll compute trace of m to the 2k at genus 1. Okay, so we can do that now. So where are we going to do that? Do that over here. Any questions in the meantime? Okay, so now what we want to do is we want to compute trace m to the 2k at genus 1. It's connected in the GUE. So the GUE is this Gaussian matrix model. So what do? Take minus the residue as z goes to 0 of x to the 2k of z times w g1 g equals to 1, n equals to 1. So this is a totally explicit thing, right? This just means z1 plus 1 over z1 to the 2k. So you just expand that, and you can compute this residue. We don't need to sit down and do it for very long. We're not going to do it. I'm just going to tell you the answer here. Okay, so if you find this, you will find that it is equal to minus 1 over 12. So now let's just double check this. So if we trace m to the 4, so trace m to the 4, connected, genus 1, so this means k is equal to 2. So let's just put that in. We've got 2 minus 1 over 12. 2 times 2 factorial, 2 factorial, and 2 minus 1, so 1 factorial. Okay. So 1 over 4 times 3, and here you have a 4 times 3 times 2 factorial, right here, 2 factorial. Let's cancel, the 4's cancel, and the 3's cancel, and we're left with 1. Great, right? It's very satisfying to see. So what was that 1? That was precisely this one single diagram we did here. But now you can see how here we were able now to extract it for general K. Now try to compute all the combinatorics of the diagrams that have this toric topology, but that always have these 2K vertices. Okay, it's a hard combinatorics problem. And the solution to the combinatorics problem is precisely this. I'll let you in with one little cool thing. That actually this is a famous result in math for very different reasons. This single trace m to the 2k at generic genus G had actually been computed via some very hard combinatorial work by Zagier and Haar, and it was related to the Euler characteristic of the moduli space of one punctured Riemann space. A very cool result. And so actually this result is also known sometimes as the Haar-Zagier formula. And now we can compute it really simply. So, as you can probably imagine, their paper was much longer because it was not just doing a single one residue integral. Okay? But topological recursion makes this very hard computation totally doable. Okay. So any questions about what we just did? Very good. I think a bit about what we want to discuss. 50 minutes. I think we'll
What is K? The Razagier formula, you just have G.
Yeah. You need to send k to 0. Like, you divide by, you mean the exact relation between here? Yeah, let me check.
I mean, on one side there's a K and not a
Yeah. No, that's right. It's the boundary of the, it's the boundary length of the, so here there's no boundary length, but really what they did was times r plus. So in this case, they're just integer valued. So it's really more like the open moduli space where you also prescribe the length of the boundary. And the length of the boundary here is 2k. Okay, so very good. Let's get to our next example. And now we're going to go back to this quartic matrix integral.
Is it a coincidence that if you put k to 0, you get minus 1 over 12?
That's precisely that. Okay. Let's now discuss resumming infinitely many finite diagrams. Feynman. Okay. Unclear with the Feynman. Infinitely Feynman diagrams. So this is one of the things I promised you in the abstract of these lectures, so I would like to deliver on that promise. And so what we're going to do is we're going to understand how we can compute something like what we did. So trace m to the 2k at genus 1. Or, for example, a 3-point function. Genus 0. So connected. But we want to do this in the quartic matrix integral. So just remember what this means is that we're trying to compute in an integral of this form squared plus this perturbation parameter we had yesterday. And so what that means is that we want to insert these various guys into this integral and then compute it as a function of lambda. And that's in general a very hard problem, right? So as we said yesterday, one way to do that, so if we put this observable O, so O could either be trace m to the 2k, or it could be all of those guys. So whatever we introduce over there, this would be the same as doing this integral in this Gaussian. O, but now we could have infinitely many insertions here. So we would have minus n lambda to the s, over 4 to the s, trace m to the 4 to the s. So as we were mentioning, this is now a complicated problem, right? Because this is this in the GUE.
There shouldn't be a trace before m to the 4 in the expression, because you're already taking the trace of the whole thing. So the purple trace should be removed.
Oh, yeah, makes sense. So again, this is the purple stuff, huh? So this comes just from expanding in the exponential. So, right, so this computes technically many, infinitely many products trace m to the 4. So if we, for example, took O just to be trace m to the 2k, okay, you can see that this requires now infinitely many complicated correlation functions. Right? So this could be, for example, trace m to the 2k. We just computed. That would be the same answer as over there. But now we would need to compute something like trace m to the 2k, trace m to the 4 at some genus G. And then here, trace m to the 2k, trace m to the 4, trace m to the 4, etc., etc. Okay? So you can see this is infinitely complicated in some sense, right? Each one of these has some Feynman diagram expansion, and so we're going to resum infinitely many Feynman diagrams by computing this as a function of this lambda. Okay. So topological recursion, we're going to see, is not really much harder or easier for the GUE or for the quartic matrix integral. Okay? So all of that formalism that we worked hard to develop, the reason why we worked so hard is that once we have this formalism, it doesn't really matter the type of problem that we're trying to solve. It's always a kind of universal type of tool. Okay? So all you need is basically the beginning is the spectral data. Okay? So we just ask, what is the spectral curve of the quartic? And again, we'll use this one-cut assumption that I mentioned yesterday. Again, I know that everyone computed y of x yesterday, so yesterday we would have this y of x, this polynomial being 0. I'm guessing no one actually computed
Minus v prime of x times y.
Yeah. The important part is what y is as a function of x, right? So I'm going to guess no one did it. That's fine. But I'm going to assume you did and just write down the spectral curve for a second. So it's totally fine. It doesn't really matter for what I'm about to tell you, how you actually really get it. I'm just, for all intents and purposes, I'm just going to write it down for now. So it turns out x always is going to look the same, actually, for any type of potential, as long as we're in this so-called one-cut phase. So it always looks something like this. Z plus 1 over z. Okay. And y has some expansion with some variables of this form. Okay. And I'll tell you what this alpha and this gamma are. So these are going to be functions of lambda. So these actually depend on this lambda parameter. Okay. What these two things mean are basically, they roughly correspond to the, in terms of the eigenvalue distribution, they correspond to the off-center, this is alpha, and this width is basically gamma over 2. Okay, so for those who think about RMT, it's roughly telling you just about geometric properties of the eigenvalue distribution. For now, you can just think of them as numbers. So this alpha is 0 when the matrix model potential is even. And these UKs, you can define, we'll leave that as an exercise, but you can find them as follows. So if you plug in v prime of x of z, okay, it always is symmetric under z goes to 1 over z. So it's going to have some expansion that looks like this. UK, z to the k is 1 over z to the k. And these UKs are precisely this, well, bad color choice. These UKs are going to be precisely the same as these UKs.
Sorry, but can we close the window because it's the sun's?
Ah. So I will close these. Yeah, the stall should just be the.
Okay, no, yeah, no, fine. Oh, it's working.
Okay, good.
Thank you.
Okay, so I'm just telling you this is a generic way in this one-cut assumption to compute the spectral curve of an interacting matrix model. It's not too important. I'm just now going to give you the answer for the quartic. Okay. So we're going to find it for the quartic model. We can write down a specific spectral curve. Z. Okay. And this gamma is just a very convenient combination of this lambda that keeps appearing. So gamma squared is 1 over 6 lambda. So let's already see how there's some resummation going on, right? So this is a full function of lambda that's popping out over here. The same lambda over here. Okay. We're not writing this as a power series in terms of lambda. We're writing it as a full function of lambda. And actually, here's a cute fact. Does something go wrong here when lambda takes some particular value?
So you wrote gamma squared equals this?
Yeah.
Okay.
So what happens when gamma hits 1 over 112? Sorry, 1 over 12. Okay, and as it keeps going,
Complex.
it turns complex. Now, we saw that this is basically the width of the eigenvalue distribution. Should that ever become complex? No. Okay. So there's a singularity that's happening here. Develops precisely at lambda equals 1 over 12. What do you think that is, given some of the discussion we had yesterday about perturbation theory? So in our first little baby integral, when we were trying to introduce Feynman diagrams, we did this thing where we switched the integral and the summation, where we expanded the exponential. And that gave rise to what type of series? Asymptotic series. Now, asymptotic series have zero radius of convergence. Right? Remember then we talked about one of the beauties about the Stoft expansion is that at every order in N, we actually had a convergent expansion in the Stoft coupling because there are just not that many diagrams of a given genus. What we found is that we have a convergent expansion with a finite radius of convergence. So what do you think this 1 over 12 is then, given what I told you?
That radius of convergence.
This is precisely, actually, the finite radius of convergence. In the Stoft expansion. It's very cute to see. So we'll see that all of our WGNs actually have a singularity as lambda goes past 1 over 12. It's very nice to see. Okay, so what we could do is we could then compute this recursion kernel in the very same way. So we would have, so B is going to remain the same. B, Z1, Z2. Okay. So this is now the spectral curve for the quartic model. So now you have everything you need to define this recursion kernel K, and then run topological recursion. So for example, I'll give you 2 answers. So we don't need to do the same type of computations because they're basically identical. And you can, for example, find something very cute. So you can, for example, find, so this is run topological recursion. We can do 2 things. So we can, for example, find W03. And this ends up being minus 1 over 2 gamma y prime z equals to 1. But this is as a full function of lambda, and of course y is as a full function of lambda. So this is a full function of lambda. So from this W03, what can we compute? By doing the same type of residues, we can compute this guy. Right. We take residues as x goes to infinity, x to the 2k1 times that guy, x to the 2k2 times that guy. We could expand and we could calculate this correlation function. But now we've calculated it as a full function of this coupling. Right? So we've resummed the infinitely many Feynman diagrams that happen in this expansion. Extremely powerful. It's something we really usually can't do in quantum field theory. Okay? So this is a really beautiful, beautiful idea. So people for a long time, going back to early days in gauge theory, thought about some sort of non-perturbative loop equations that come from Schwinger-Dyson equations. Okay? And that somehow their solution would be non-perturbative in the coupling. So the coupling is very large in QCD. I know I'm saying some things that mathematicians maybe not appreciate, but basically this lambda for us ends up telling us about the strength of certain forces in physics. So things at CERN, unfortunately, the forces that that we have to deal with are actually very, very strong. Okay, it turns out. So that when things are very, very strong, this lambda is very large, you can see that doing standard perturbation theory in lambda is not very good. Right? So the whole idea was to try to come up with new ways that were able to kind of capture the full dependence on the strength of this interaction on this lambda. And so topological recursion is kind of a very precise mathematical realization of one of those ideas. Okay? It allows you to compute observables as entire functions of this lambda, not doing just a little Taylor series. That's a really, really beautiful thing. Okay, so in the last, maybe any questions about this?
Sorry.
I mean, you just talked about big lambda, but this procedure is still limited to lambda less than 1/12.
Yes, of course.
But so for big lambda, we have to do something else, or I mean, maybe optimize this procedure.
Yeah, sorry. So I think maybe depending on the sign, it'll either be at minus, for the physical realization, there's an extra sign here, and then it's at minus 1/12, so we can take lambda very large.
Okay,
Yeah.
So far we've only computed at genus G equals 0, but strictly speaking, to get the actual expectation value, we'd need to get the other additional genuses.
Yes.
Yeah.
But we've already done an example where we computed something here, at, for example, genus 1.
No, it's not about the genus, it's about whether it actually converges eventually with all the...
So that never converges. So there's no free lunch, like you don't start out with something that had a non-convergent expansion, and then somehow you end up with the convergent expansion. Okay, that's not true. But the idea is that if you take some observable, and we can expand it in these 2 power series, so one of them is the 1/n expansion, it's G, and then the other one was this expansion, CG, let's call it number of vertices, lambda to the V. Okay. So this, as I was saying, defines some function at each order in 1/n as a full function of lambda, again with a finite radius of convergence, so say like this 1/12. But this expansion over here, this guy is still a asymptotic. Okay. So it's still not that we know O as a full function of this coupling. Okay. At each order in n, we can do that. Now, this is usually pretty good, even for something like at CERN, if we could set something up like that. So for us in CERN, we look at matrices that are 3 by 3. Okay. So it's an expansion in 1/n squared, right? So the first term already is going to be suppressed by basically 1/10. Okay. And the next guy will be 1/100. So this, pretty quickly, you're in the percentile to sub-percent accuracy, if you can do just even the first few orders in 1/n. But you have this as a full function of this coupling, which is really unheard of other. Okay, so that was kind of the main idea of people of doing this 1/n expansion. Answer your question? Yeah, great. Okay, any questions about this? So now I think what I'd like to do in the last half hour is
We still have an hour.
Huh?
We still have an hour.
Well, I might be generous with you guys too.
Thank you.
Yeah.
Pretty mad.
So we might discuss, I think, just some general applications of topological recursion beyond matrix models. So here what we did is we sketched kind of the history, starting from Schwinger-Dyson equations into this topological recursion equation. Now we've seen how you can actually use it and compute, okay, get your hands dirty a bit. But now what I'd like to do is to tell you that this subject has sort of taken a life on its own, and that topological recursion actually governs many, many problems in mathematical physics. And the way that I'll convince you of that is just giving you a few examples of totally different type of problems that all satisfy topological recursion. And basically all you have to do is to specify the spectral curve. And once you have the spectral curve, you can spit out all of these various things. So we're going to be discussing some objects that are probably not familiar to you. And the point of the rest of this lecture is just to kind of tell you about some cool stuff. Okay, it's not really for you to know the precise definition of all these objects. Those would be whole summer schools in themselves. But I'll just kind of mention a few of these things. If you have any questions, now's a good time.
Life. What's the meaning of life?
That I'm not good. Maybe I'll tell you that in the remaining 30 minutes.
You have to get this Z bar.
Also 42.
I concur.
Can I ask a question on you, Mr. Board? You said that this Z bar is obtained where x of sigma of z equals x of z. Is it always that we have one particular point?
No, so usually it's only defined locally around each ramification point.
Okay.
So it happens here that there's a globally defined.
So in mass level, you take the residue essentially.
Yeah, so if you want, usually there's an expansion in a local coordinate. So we could define x of z locally as x of a at some local coordinate squared. Okay. And then the involution is just
Yeah.
zeta goes to minus.
Yeah, okay.
But in this case, we had something globally defined. So.
Is there some physical interpretation to this radius of convergence though? Like, you're saying it's a negative coupling.
Yeah. So n equals 4 reciprocating Mills has basically the same type of issue. Yeah. I guess it would be some sort of instanton proliferation, basically. So when you're at the edge of the radius of convergence, you get all these non-perturbative effects that become very important. Yeah. Okay, so let's talk about a few nice examples. Okay. So we'll talk very quickly about an example that won a Fields Medal. We're going to talk, now we're going to applications of topological recursion to beyond matrix models. Maybe as the very last one, I'll tell you about how this connects to work I've been doing in the last few years. So, we drew a lot of pictures of various surfaces like this. Okay. And so we gave them a genus and these labels. These were the boundaries of these surfaces. And actually, if you what we can do is we can assign a particular length to each one of these. So I'm going to tell you with respect to what metric, because if not, he's going to ask. So we can take these Riemann surfaces and we can always put a hyperbolic metric on them. Okay? So it's a metric of constant negative curvature on these surfaces. And so with respect to that metric, these are going to be geodesic boundaries. And then we can compute the geodesic length with respect to that metric. That I'll call L1, L2, L3, L4 in this particular case. And it turns out that the number, if you want, okay, there's a finite dimensional space of the Riemann surfaces with this hyperbolic metric and these boundary lengths, L1 through Ln. And you might have thought there's infinitely many of them. It's true if you were trying to imagine counting each one, but there's a finite dimensional space of them that you can parameterize, okay, that has a fixed dimension that depends on G and on N. And one thing you can do is it turns out that this space actually is a symplectic space. And so there's actually a notion of a symplectic volume. So maybe you've seen this sometimes in the phase space, say just of a single particle, where we can write a form dx dp, wedge dp, on phase space. Okay? And then what we can do is we can ask about volumes in phase space by integrating over some area in phase space, this volume form, dx wedge dp. So one thing we can do is that we can imagine asking, what if we integrate over this space with a particular form? And there's a particular symplectic form on here, which is called the Weil-Petersen form. Weil-Petersen symplectic form. Okay. And so these define particular volumes of the space of these surfaces that depend on the boundary lengths L1 through Ln. Weil-Petersen, L1 through Ln. So Mirzakhani was a really brilliant mathematician, and she found a recursion relation on precisely the Euler characteristic, this 2g minus 2 plus n. Hani's that allowed to compute these basically recursively. Okay. Maybe so. I have another label. Gn. And this one or the partly the field's metal. Okay, so this is a very, very hard problem, and it was very surprising to people that you could compute these recursively. So computing each one by hand were papers in their own, and people had only done maybe genus 1 point or something like that. Okay, so they were very hard problems to do, and then she found this beautiful recursion relation. What we're going to see is that this is a special case of topological recursion. Okay. So there's going to be a particular spectral curve that actually spits out these volumes. So in fact, it's not going to be precisely the volumes, it's going to be a Laplace transform of these volumes. So I'm going to tell you what the WGNs are for this particular problem, then I'll tell you what the spectral curve is. So let me just give you a few of the first ones. Okay, so W03 of L1, L2, L3. Just giving you a few examples. So this one is 1. Okay, W11 of L1 is L1 squared plus 4 pi squared over 48. Okay, I'll give you one more. That's a half. So now what we're going to do is we're going to define a Laplace transform of these guys. So this z is going to be the Laplace conjugate to this variable L. So this will look like -1 to the L, Li dLi, 1 to n, e to the minus zi of these volumes. So I'm just going to define these right now as the WGNs. Now, the thing is that these WGNs satisfy topological recursion. So that is really the topological recursion with the WGNs is equivalent to Mirzakhani's topological recursion. WGNs. Really, really beautiful, surprising fact. And so what we can do is we can just tell you what the spectral curve is going to be. And maybe we can even compute one of them. Let's see what's the... Yeah, we can compute W11 if you want. So the spectral curve. And physics people who maybe have heard of JT gravity, the Saad, Schenker, Stanford matrix model, this is really at the heart of it. That was their realization that there was some connection between 2D gravity and matrix models, and JT gravity and matrix models. So here's the spectral curve. here we go. And same Bergman kernel as always. Very good. So, let me just tell you, for example, we can compute by doing the exact same exercise. So same computation we did before, but just now with different x, y. And you would find, for example, that W11 Z is, here it's quite simple. There's actually only one branch point, right? So dx of z is 2z dz. So there's just a single ramification point, z equals to 0. Okay, so you just do the same computations we did, and you take residues instead of at +1 and -1, you do them at z equals to 0 here. And you would find that this is 3 plus 2 pi squared z squared over 24 to the 4 dz. Now you can plug that in, do the inverse Laplace transform, and lo and behold, you will find precisely that volume. Okay, so it kind of had to be true given what I told you. But this spectral curve was totally not known. So Maynard and Arentin, they really kind of played around, and it turns out you only need a certain order of the Taylor expansion of y around the branch points to get the right answer. So you can just try to put some series expansion, compute it as a function of that series expansion to see what you would need to get the right answer. You compute this a few times, and they started realizing that, oh, wait, this is the series expansion of sine. Okay? And then later they were able to show that this is true for all w, g, and n by essentially taking the topological recursion equation and inverse Laplace transforming it. Okay? So if you have a recursion relation for the WGNs and you have this relation here, then you can find a recursion relation for these volumes directly. And they showed that was precisely the recursion relation of Mazenc. So this just goes to show you that this is something much more broader than just about matrix models. So it started life as matrix models, and the 1/n expansion being the topological expansion. Here the topology is just kind of God-given to us from the topology of these Riemann surfaces. And it gives rise to these type of problems. Okay? So I'll give you just now, in less detail, maybe 2, 3 more examples, and then I'll do a final statement about some connection to modern research. Okay. So some other examples. Okay. So examples. Okay. So this is what's called the Airy curve. This is x equals to z squared, so just like over there, and y just equals to z. Okay. So it's airy because y looks like square root of x, which is the airy behavior in WKB approximations of the wave function near a term. Anyways, so what this computes, so the WGNs here, they compute again Laplace transforms of what are called intersection numbers. And I'll tell you what these things are very briefly on MGN. So basically, this moduli space of Riemann surfaces keeps popping up. This one's a little slightly different. This is the moduli space of Riemann surfaces. It's not quite the, so this is endowing it with the complex structure. It's not picking a particular metric nor giving boundaries, but it is what it is. And these particular numbers were quite famous due to the work of Witten and Konzevich. So there's a particular type of integrand. So there's particular forms on MGN that you can define. Again, their precise definition is not going to be too important, but they're called psi classes. And you can wedge them to some particular power. Okay. And this defines some integral. So these are particular two forms on a space which is 2 times 3g minus 3 plus n dimensional. So MGN is a 6g minus 6 plus 2n dimensional space. There are two forms. You can wedge two forms until you get a top form. You can do this integral. And so these are particular numbers that depend on k1 through kn. They're called intersection numbers because I'm going too far. But you can map forms to particular surfaces by Poincaré duality, and what this is computing is actually how many times these various surfaces intersect. Okay, so there's some geometric meaning to these numbers. And this was quite famous in the 90s, so physicists care about this because these end up being the correlators, in some sense, the kind of stupidest string theory you can imagine. And what Witten had conjectured in the 90s is that a certain generating function of these numbers actually obeyed some integrability conditions. It's called the Witten-Konzevich theorem. It was proved by Konzevich, and that won him the Fields Medal. Okay, so there's a lot of various field medal level math problems that all end up being solved by topological recursion. Okay, so we're starting to see that it's actually this extremely powerful tool that goes well beyond the little matrix models that we started with. So maybe in the last 10 minutes, I'll give you some physics musings and tell you how this is connected to my own research. So as you see, there's this connection to the moduli space of Riemann surfaces that keeps popping up. And that's not surprising given the type of pictures we keep drawing, which is that of Riemann surfaces with some genus and some n, right? So when physicists think about those type of problems, the reason that they think about Riemann surfaces, one reason is that they think about strings. Okay? So maybe before we go into that, you can ask me your question.
I wanted to ask, is there a reason why Laplace transforms appears often in this problem?
It's a good question. I don't think anyone really has a very deep reason why somehow the Laplace transform of a lot of these quantities tends to be the right one.
Like in general, why do you need to do like a transform to get the recurrence relation?
I don't have some one phrase answer as, you know, it's always the Laplace transform. I think it's something that puzzles people. The structures of the recursion relations are always a little different. Topological recursion is also a little different from these type of things where, in fact, the base cases, as we said, were for g equals to 0, n equals to 1, and g equals to 0, n equals to 2. Right? This is the information of y, x, and b. And often these type of quantities, you see, I didn't write them down. And it's because they often don't make sense for those values of g and n. They're what are called unstable values of g and n. The moduli space of Riemann surfaces doesn't make sense for M01 and M02. So in some sense, topological recursion is kind of starting with some sort of object that, if you tried to define it directly in terms of these objects, wouldn't really totally make sense. So it's a little hard to say. But I don't have a good answer. I don't think anyone really knows.
If I'm not mistaken, Mirzakhani also proved Witten's conjecture. Was this also part of her proof?
It turns out that proving proof of Mirzakhani's relation also gives you a recursion relation on the psi class intersection number that you can then map to integrability. So, yeah. Questions? So let me now mention some connections to some more physics. I think you guys got enough physics. Yours probably has the most physics out of all of them. some more chickens. Oh, and the quantum info. Sorry, I take this back. Some more high energy. Okay. So maybe one place that you can ask is there always some sort of connection between topological recursion and this moduli space of Riemann surfaces? Okay. So is there always... bar is about some factorification of this moduli space. And the answer is yes. And this is due to some work of Einard, and then also plus other collaborators, Doss, so Dunborowski, Orantin, Shadrin, and Sarkovsky, I think. And basically the idea is that all of these WGNs always can be written as some particular integrals over MGN with some particular integrand. So they always have some sort of relation between the two. With, of course, some integrals that depend on Z1 through Zn. Just because this is a function of Z1 through Zn. Okay, so in the Airy case, for example, let's look something like this. Airy. Get some of the factors wrong. So this is one example where we sum over all these cases. Okay, so this was one example in the Airy case. But there's always some integrand that you can write down. Okay? So you can ask, now, physicists, they think these integrals over MGN, so physics intuition, is that integrals over MGN have some relationship to string theory. And roughly, why is that? So when we think about particles, when we think about the quantum mechanics of particles, one way to calculate things in quantum mechanics is to imagine that this particle can do any possible thing given some boundary conditions at two different times. Okay? This gives rise to what are called path integrals. Okay? So if we had a zero-dimensional particle, as it moves in time, it sweeps out something with one extra dimension. And we call these things world lines. Okay. Now, what happens when we have a string? Okay, so the basic idea of string theory is that we start with not a particle, this guy over here, okay, but now a string. So as these guys move in time, what happens is that they sweep out a two-dimensional surface. Right? So we have one dimension here, plus another one of time. This gives a two-dimensional, what we call the world sheet. And what these strings can do is they can kind of split and join. So at some point, for example, the string might do something like this. Okay? And in that case, okay, the world sheet will end up looking, well, it'll look like this string comes, it splits, and then maybe they recombine. So you can get a Riemann surface of some genus G. And the various n, the 1 through n, they can be the boundary conditions that you give on these world sheets. So here we only looked at things with two boundary conditions, but in general we can look at surfaces that have more boundaries. just like we were saying with Mazenc. So then you can ask, well, given a topological recursion, can you imagine some string theory that reproduces those integrals over MGN? So why are we doing an integral over MGN? We're trying to sum over all possible surfaces. Right here we're trying to sum over all possible trajectories. So this space over all possible 2D Riemann surfaces is basically summing over all ways that the string can propagate. Okay. So this here comes from the path integral. That's why when physicists see these types of things, they imagine some sort of string theory coming up. And some of the things that we've been working on is to precisely ask, given a spectral curve, so given x and y and this b, what is sort of the string theory that gives rise to these WGNs? Again, that's an integral. And here we have an early answer. So they are a particular type of strings. They're very simple, so they're called topological strings. And it turns out that all of those quantities over there actually have meanings in the string theory. So in the string theory, these are called B-twisted Landau-Ginzburg models. And to define these theories, you need actually also two objects, basically. So one of them is going to be some sort of potential. Okay, it's called the superpotential. And that is going to be identified with this x of the spectral curve. So these strings are going to move in a space that is precisely the spectral curve. Okay? So the place where these strings are moving is the spectral curve. There's a potential for these strings that's equal to this x. And the spectral curve is the simplest example of a complex manifold of one dimension. And as Nikita had mentioned, there's a top form, omega, which is nowhere vanishing. And this is what we take as dy. So in this particular case, there was a very nice mix of kind of complex geometry, string theory, that also has now a connection to topological recursion. So it's a really very, very, very rich subject and allows you to be very precise, as you can see, with the sort of things that we calculate.
Is the correspondence bijective or is it more restricted?
Here was to find a string theory that reproduces everything from a topological recursion, that all the WGNs are equal. I don't really know what else you would mean on the TR side.
Given,
maybe there's some things you could compute here that you can't compute here.
not that. Given an arbitrary topological recursion, can you always find a string theory or vice versa? That's the question I'm asking. Is the correspondence bijective?
I don't think we understand the correspondence well enough to answer that question.
Thank you very much.
Okay, so any questions here about these things?
When you say string theory, what exactly do you mean? Do you mean the form you're integrating over MGN?
No, so I mean a little more. So usually we would want to define some sort of action principle for a string theory, and we write down some two-dimensional field theory that lives on this two-dimensional surface, and we can really do something like that.
Okay. Yeah. So integrating these fields over these dimensions, these Riemann surfaces. Okay.
And then you integrate over all the surfaces.
Then you integrate over all
the last step in the path integral.
Okay, okay.
Okay, any more questions?
Can we do the same thing as for matrix models for SUN gauge theory?
That's the million-dollar question. Yeah.
I guess we don't know.
So, Schwinger-Dyson equations get much, much more complicated. And in some sense, we don't really know how to solve those Schwinger-Dyson equations. But, I mean, kind of at the most superficial level, people had kind of gone to matrix models as little toy models of gauge theory. And this would be like solving these Schwinger-Dyson equations, these group equations. No, I mean, we're nowhere near being able to do that for full Even like two-dimensional Young-Mills or something is still, So I'm not saying there's no chance, but
At the moment.
I think it's a good tool for physicists to be aware of and to maybe try to find applications in higher dimensions. But things get complicated pretty quickly. So, great question.
Practice, what is the hardest step? Is it finding the spectral curve, the hardest step? Or computing, I mean, the residues, I guess, you can just do it computationally.
Yeah, so those you can do on a computer. Of course, as you go to higher and higher genus and n, there's more and more terms you need to do, and you need to do it recursively, so there's more and more things you need to compute. So of course it gets hard. So you know, genus 17 or something, like there's a lot of things you need to put on the computer, but usually you can do. Usually it's more about setting up the problem. So it's finding, given a particular enumerative geometry problem, some combinatorics problem, how do I set up a spectral curve that does that? So we found the Schwinger-Dyson equations in the matrix model, but you know, when you're starting from something totally different, you have to think about it.
So find some Schwinger-Dyson equations for that problem in a way.
Yeah, so an example, for example, doesn't usually come, or people don't think of it from matrix models, are like Hurwitz numbers. So these are coverings of the sphere by a Riemann surface. It's in genus G. And there are so-called cut and join equations. I'll tell you about relations between these Hurwitz numbers. And for example, those can be, they can give rise to a spectral curve. In fact, their Laplace transforms ends up being equivalent to these kind of general equations. So, yeah.
What makes matrix models this special to get the spectral curve? Like, is it a generic property or?
Well, so many problems have spectral curves, right?
Oh, this I agree, yeah.
Yeah.
So is there an underlying principle in some sense that we know would generate this spectral curve, or is it just a trick that we introduce?
I think we don't know yet. So I think yeah, different problems have different spectral curves, and how you generate those is usually hard. It's to find some sort of relations between W01, W02. So you have to be clever. The spectral curve is anything else? Okay. If not, I think we can have an early start. You'll learn more about TFTs tomorrow, and even some Stokes phenomena. So you'll see about some things about non-perturbative physics and e to the minus 1 overcoupling, corrections. There's still a lot of things that to be learned for the rest. So thank you very much.